Hey there, tech enthusiasts. Welcome to Martyr Debugger, where we simplify code, debug concepts, and make computer science fun. Let's dive in. Hi, and welcome to this video on concurrent programming in Java. In this video, we will explore what concurrency is, how it is implemented in Java, and why it is so important in the world of software development. Concurrent programming allows us to execute multiple tasks simultaneously, optimizing system resource usage, and improving application performance. We will look at practical examples and real-world situations where concurrency plays a key role. Before diving into technical details, let's consider some real-life examples where concurrency is crucial. Google Chrome runs each tab as an independent process, preventing an error on one page from affecting the others. Web servers like Apache and Nginx handle multiple user requests simultaneously using waiting threads. In video games, graphics engines use threads to manage physics, rendering, and sound at the same time. Now that we understand why concurrency is important, let's take a closer look at how it works. In the next example, we are comparing a sequential and a concurrent program. Let's start with the sequential one. The program calculates the sum of squares of the first n natural numbers using a single thread. Let's break it down. The program starts by defining the value of n, which represents the number of elements we will process. In this case, we set n to 1 million. Next, we initialize a variable called sum to store the result. Then, we measure the start time using system.currentTimeMillis to calculate how long the program takes to execute. We then use a for loop that runs from 1 to n. In each iteration, we calculate the square of the number and add it to the sum. Since this loop runs sequentially, each step must be completed before moving to the next one. After the loop finishes, we measure the end time and calculate the total execution time by subtracting the start time from the end time. Finally, we print the sum of squares and the execution time in milliseconds. This approach is simple and efficient for small tasks. It does not require complex thread management, making debugging easier. However, for large datasets, a sequential approach may become slow because it does not take advantage of multi-core processors. Now, we will explore the concurrent version. Our program begins with a definition of the SumThread class. This class extends the thread class, meaning each instance represents an independent thread. Inside SumThread, we declare two variables, start and end, which define the range of numbers each thread will process. We also have a variable called partial sum, where each thread will store its computed sum. The constructor of SumThread takes two parameters, the start and end values for the range of numbers this thread will process. The run method contains the logic of the thread. It iterates through the assigned range, calculating the square of each number and adding it to partial sum. This method is automatically executed when we call start on a thread. At the end of the SumThread class, we define a method called getPartialSum. This method returns the sum calculated by an individual thread so that the main program can later combine all results. Now, let's move to the concurrent class, which contains the main method. We start by defining the total number of elements, n, and the number of threads, number threads, that will divide the work. We create an array of SumThread objects, where each thread will be responsible for processing a portion of the numbers. we calculate the range of numbers that each thread will handle by dividing n by the number of threads. Next, we record the start time using system.current_time_millis, so we can measure the program's execution time later. In a loop, we create each sum thread and assign it a specific range of numbers. Then, we start each thread using start, which runs the run method in parallel with other threads. Inside the loop, we calculate the start and end values for each thread. These values define the range of numbers the thread will process. The start value is calculated by multiplying I by range, the range each thread will handle, and adding 1 to it. This ensures that each thread starts where the previous one left off. The end value is calculated using a ternary operator. If I is the last thread, I equals number threads 1. It processes all remaining numbers, so we set n to n. Otherwise, each thread processes its assigned range, calculated by I+1 * range. Next, we create a new instance of the SumThread class using new SumThread start end. This calls the constructor of SumThread and passes the start and end values so each thread knows what part of the task to execute. After starting all threads, the main program waits for them to finish using join. This ensures that all computations are completed before proceeding. Once all threads have finished execution, we retrieve their partial sums using getPartialSum and add them together to obtain the final sum of squares. We then record the end time and calculate the total execution time by subtracting the start time from the end time. Finally, we print the sum of squares and the total execution time in milliseconds. By using multiple threads, we distribute the workload across multiple CPU cores, potentially speeding up execution. However, creating and managing threads adds overhead. If the workload is too small or the number of threads is not optimized, the concurrent version may not be faster than the sequential version. As I've told, sometimes the concurrent version can be slower than the sequential one, and this is the example. Let's increase the n so you can see that now the concurrent one is faster. Let's now focus on different syntactic concepts. You can create threads with two alternatives. Let's start with the runnable approach. The first line of the code shows implements runnable. This means that the class is agreeing to implement the runnable interface, which requires us to define the run method. The run method is where the actual task of the thread is defined what the thread will do when it's started. Next, we move to the public void runLine. This is the method that gets executed when the thread starts running. Inside the run method, we define what happens when the thread runs. In our case, we just print a simple message. This is the main part where the thread's action is described. Then, we get to the public static void main string_args method. This is the entry point for running the program. Here, we are creating a new instance of the thread class and passing an instance of our runnable class to it. This is done in the line new thread, new Ola runnable at start. Notice that by using new thread, new Ola runnable, we are creating a new thread object and passing our Ola runnable class as the task for the thread. The start method is then called to begin execution of the thread. Now let's look at the second approach, which is extending thread. The first thing we notice is extends thread. By doing this, we are telling the class to inherit from thread which already has the run. method that we can override. Again, inside the run method, we define the task for the thread, just like we did with Runnable. The key difference here is that we don't need to implement Runnable, since we're already extending thread, which provides the run method. In the main method, we create a new instance of OLA_thread and call start on it to begin the thread's execution. This is similar to what we did with the Runnable approach, but here we directly create a thread object by extending the class. To sum up, the main difference in syntax is that with Runnable, we use implements to provide the task for the thread, while with thread, we use extends to create a subclass of thread and override the run method directly. And that's it. With Runnable, we have more flexibility, and with thread, it's a simpler approach if we don't need additional inheritance. Let's now talk about anonymous classes in Java, which are a great way to implement functionality without creating a named class. When using an anonymous class, we don't define the class name explicitly. Instead, we create an instance of a class and, at the same time, define its behavior. This is done by using a simplified syntax where we directly pass an implementation of an interface or extend a class. Let's look at implementing Runnable using an anonymous class. We don't need to create a separate class. Instead, we create an instance of Runnable directly in the thread constructor without the need for a named class. Here, we define the run method in place, right inside the thread constructor. This way, we don't have to explicitly define a class, but we still implement the Runnable interface. Now, let's talk about extending thread using an anonymous class. Instead of creating a separate thread class, we can also create an anonymous subclass of thread. We use a similar approach. Inside the thread constructor, we directly extend the thread class and override the run method in place. In both cases, we skip the step of explicitly naming a class and instead define everything inline. This results in more compact and less cluttered code, especially useful when the behavior is simple or only needed for a one-off task. Let's see another example. Here we have a class called T that extends thread. The class has a constructor that accepts an integer n and stores it in the n field. This is how the thread can have a unique identifier or value assigned to it, which helps us track which thread is running. In the main method, we have a loop that runs 3 times. Inside the loop, we create a new instance of class T and pass the loop index I to the constructor. Then we start the thread with its start. Each thread will execute the run method. Inside the run method, we have another loop that runs 5 times. Each iteration of the loop prints a message indicating the thread number, n, and the iteration number, I. Then, we call the delay method, which pauses the thread for a specified amount of time. The delay is calculated based on the thread number and +1 * 1000, meaning that each thread has a different delay based on its number. After the loop finishes, the thread prints end thread followed by the thread number, n, indicating that the thread has completed its task. Let's now talk about the two methods, delay and echo. First, we have the delay method. This method is used to pause the execution of the current thread for a specified amount of time, given in milliseconds. It calls a built-in function to make the thread sleep for the provided duration. Next, let's discuss the echo method. This method simply prints a message to the console. Let's see another example. First, we start by printing the name of the current thread. In the main method, the first line prints the name of the current thread. Since the main method is executed by the main thread, it will output something like main, which is the default name for the main thread in Java. We use thread, current thread, getName to get the name of the currently executing thread. Next, we enter a loop that creates and starts multiple threads. Inside the loop, we create 10 new threads. Each thread is given a unique name using thread plus I, where I is the loop variable. This means the threads will be named thread 0, thread 1, and so on up to thread 9. For each iteration of the loop, a new thread is created using an anonymous inner class. The run method inside the anonymous class prints a message showing which thread is executing the code. We use thread, current thread, getName inside the run method to print the name of the current thread that is executing the task. After defining the thread, we immediately call start to begin the execution of the thread. This triggers the run method of each thread, and the message is printed for each one. Let's see another example. In this code, we have a class called threadName that extends thread. Inside the run method, we define the task that each thread will perform. The method runs a loop 3 times, and on each iteration, it calls the print message method. The print message method. This method prints the name of the thread currently executing it. We use thread, current thread, getName to fetch and print the name of the thread. This allows us to identify which thread is executing the print message method. In the main method, a loop runs 10 times, creating 10 instances of threadName. Each time we create a new threadName object, we give it a unique name using TT, setName, thread plus I. This means the threads will be named thread 0, thread 1, and so on. Then, for the first 5 iterations, when I is less than 5, the thread is started by calling TT, start. This starts the thread and causes the run method to be executed, which in turn calls print message and prints the thread's name. Let's see another example. First, we have the thread.sleep method. This method is used to pause the current thread for a specified amount of time. In this case, we are telling the thread to sleep for 4,000 milliseconds, or 4 seconds. The sleep method can throw an exception if the thread is interrupted while it is sleeping, so we place it in a try-catch block. If an interruption happens, the exception is caught, and we print an error message that includes the exceptions message. Now, let's discuss the interclass. In the interclass, which extends thread, we override the run method to define what the thread will do. The thread first prints starting, to indicate it has started its execution. Then, the thread sleeps for 10 seconds, using sleep 10,000. This is an example where the thread is paused for a long period of time. However, during this time, it may be interrupted, and if that happens, the exception is caught, and interrupted is printed. After the thread finishes sleeping or being interrupted, it prints finished, to indicate its task is complete. In the main method, we create an instance of the interthread, start it using hide start, and then immediately send an interruption signal by calling hi.interrupt. This causes the thread to be interrupted while it is sleeping, triggering the interrupted exception in the run method. The thread catches the exception and prints interrupted before continuing to finish its execution and print finished. We also print sending interruption and sent from the main method, showing that the interruption is sent and handled in real time. Let's see more interesting methods. Join waits for another thread to finish before continuing. Join with a time limit waits for a specific duration before resuming execution. Interrupt signals a thread to stop, but does not force it to do so. Current thread retrieves the currently running thread. IsAlive checks if a thread is still running. Yield allows the thread to voluntarily pause and let others execute. Let's break down this code step by step, focusing on its syntax and execution. First, we define a class that extends thread. This means that each instance of this class represents a separate thread. Inside the run method, we define what the thread will do when it starts execution. The first line inside run prints a message indicating that the thread has started. The thread's name is retrieved using current thread, getName. Next, we call yield. This method allows the thread to voluntarily give up its CPU time, allowing other threads to execute. However, yielding is only a suggestion to the scheduler, meaning the thread may continue running if the system decides not to switch execution. Then, the thread calls sleep 10,000, making it pause execution for 10 seconds. Since sleep can throw an interrupted exception, we place it inside a try-catch block. If an interruption occurs while the thread is sleeping, execution moves to the catch block, where we print a message indicating that the thread was interrupted. If the thread completes the sleep without being interrupted, it prints a message checking if it is still alive using current thread, IsAlive. Finally, at the end of the run method, the thread prints finished along with its name. Now, in the main method, we create two instances of the interclass, naming them worker1 and worker2. Both threads are then started using start, which triggers their run method in parallel. Immediately after starting the threads, we print a message stating that we are sending an interruption. We then call interrupt on the first thread, attempting to stop it while it is sleeping. After this, we call join on both threads. This ensures that the main thread waits for both worker threads to finish before continuing execution. If an interrupted exception occurs while waiting, it is caught, and a message is printed. Let's break down the explanation of this Lambda notation and thread creation. First, we define a runnable using an anonymous inner class. In this approach, we create an instance of runnable using the new keyword and override the run method inside curly braces. This is the traditional way of implementing a runnable, where we explicitly define the method within an anonymous class. Next, we use a Lambda expression to simplify the syntax. A Lambda expression allows us to define the same behavior in a more concise way. The first Lambda version includes curly braces and an explicit block for the run method. This makes it look similar to a standard method definition. The second Lambda version is even more concise, removing the curly braces when there is only a single statement inside the Lambda body. Now, we create a thread using the runnable task. We pass the runnable instance to a thread constructor, storing it in a thread object and starting it using the start method. Alternatively, we can create and start the thread in a single step by passing the runnable directly to the thread constructor and calling start in the same line. To finish, let's see these last examples. First, we create a thread using an anonymous inner class. We pass a runnable instance to the thread constructor. Inside the runnable, we override the run method, where we define the execution logic. Then, we call start to begin execution. This is the traditional way of creating a thread using a runnable object. Next, we simplify this using a Lambda expression. Since Runnable is a functional interface with a single method, we can use a Lambda expression to replace the anonymous class. The first Lambda version keeps curly braces around the method body. This syntax is useful when multiple statements are inside run. The second Lambda version removes the curly braces because there is only a single statement inside run, making it more concise. The last example extends this by printing the thread's name. We use thread, current thread, to get name to retrieve and print the name of the thread executing the run method. Congratulations for watching this introduction to concurrency in Java. We covered key concepts like creating threads, using Runnable, Lambda expressions, and important thread methods. If you found this video helpful, make sure to like and subscribe for more content on Java programming and concurrency. See you in the next video.